Well, welcome everyone to today's version of the English Problems Seminar. So we're very happy to have Graeme Milton, a distinguished professor at University of Utah, to talk today. So he's a world-leading expert on composites and has produced a lot of results in the intersection of mathematics, physics, and magic. So some of his early work involved effective properties, and more recently he has worked also on turning this into very interesting inverse problems. So thanks a lot, Graeme, for joining us today.
Thanks so much, Milton. I was say, did you say at the intersection with magic? Maybe I misheard you, but I thought that was interesting. Anyway, delighted to give this seminar. This is joint work with Ornella Mattai. She's from Italy and is now in at San Francisco State University, and Mihai Putna at UC Santa Barbara. So there are both of them, and you can see on the right, Mihai, like this picture, just shows you him in Singapore and all the grading that he had to do. Anyway, many systems depend on time, and then one usually measures the response to applied fields that are often at constant frequency, or alternatively delta functions in time and space, so that one recovers the Green's function. And the question we're posing at the moment is that can we be missing something here? In other words, are there advantages to taking applied fields that have a more complicated time dependence? And we'll see the answer is yes, and that with carefully designed applied fields, the response can untangle at specific times and reveal information that otherwise would not be easily extracted. So in particular, we'd be looking at two-component composites. What do we mean by a response that's not instantaneous? We're looking at linear systems, and this could be electricity, magnetism, elasticity, but it takes a while for electrons, atoms, macroscopic currents, or displacements to respond to the applied fields. And so then the system has some memory, and there's a relationship between the applied field, if you like, or the stimulating field, and then the response field, if you like, given by some kernel, so that the current here at a time t depends upon the electric field at times t prime at a previous time. So here, essentially, you've got some sort of integral kernel, which is 0 if t prime is bigger than t. So now we're interested in two material composites, and each with their own non-local temporal response. Something's, oh well. Do you see that on my, oh. Sorry, I'm having trouble with this. This is, okay. Did I stop the share? I think I did, didn't I?
Mm-hmm.
Okay.
Looks good.
Yeah. All right. There's a sort of bar there. Okay, now I'm moving it. That's better. Yeah, so just to Oops. So oops. Okay, I had trouble with it being frozen. So anyway, you've got this two-phase composite with its response. So it's a response K1 in phase 2 and a response K2 in phase 2. So we're thinking about composite materials where you have some sort of microstructure at the microscale, and you have some sort of macroscopic response, associated with the local properties that may be the conductivity, maybe the elasticity tensor. There's an associated homogenized or effective properties. So our objective to begin with is just to determine the volume fraction of one phase in a composite or of an inclusion in a body and the shape of that inclusion. And there's many, many contributions here. Obviously, I don't have time to go into the details. The setting that we'll be looking at is viscoelastic composites. So in viscoelasticity, there's it could equivalently be conducting composites or dielectric composites. Viscoelasticity is maybe a little bit more interesting physically because the response time is a bit longer. But the basic experiment one has, one is called a relaxation experiment, where all of a sudden you take a bar of a material, for example, and then you extend it by an amount delta L, and then you look at the stress or the resultant tension in the bar, if you like, as a function of time. And then that sort of decreases as a function of time. And that's stress relaxation. And an opposite experiment is creep. And creep is when one applies a given force or tension to the bar, and then watch how the bar lengthens as a function of time. And so that's this sort of diagram here. So what are the equations? So they're basically the same as the conductivity equations, as I mentioned. This is for the case of antiplane elasticity. And so you've got some sort of geometry. This may be sort of a periodic geometry here, but you impose a displacement in the vertical direction. Your inhomogeneities have the property that they're independent of the vertical axis, so they're cylindrical in structure. And one then has this relationship between the shear, which is basically the derivatives of that vertical displacement, and the associated shear stress, which is composed of these components of the stress matrix. And the shear stress has the property that the divergence of J equals 0. And then you have, if there's no memory, you end up with this equation here. So this is J is just G grad E3, and G is the shear modulus. However, if there's memory or viscoelasticity, there's this integral kernel which creeps in. So now we're talking about composite materials, and we assume that we've got one phase that's purely elastic. So this is creep. It's purely elastic, and so it doesn't creep at all. This is the creep experiment. So it would have a response given by this straight line. Phase 1, however, does have creep, And so the creep as a function of time follows this curve here. And then we can derive bounds that show that no matter what the geometry is, that the creep must lie between the blue curve and the green curve. And this section of the blue curve corresponds to a simple layered structure. But now what's sort of interesting is that if we include additional information into our bounds, such as the volume fraction, that's the red line, or volume fraction and assuming isotropy in the transverse plane, geometric isotropy in the transverse plane, more information gives you tighter bounds. That's natural. But what's really was unexpected to us is that there's certain times like here where the bounds almost collapse. And for a stress relaxation, you get a similar sort of things. There's this sort of time here where the bounds almost collapse. And in this case, both the violence with the volume fraction and volume fraction plus isotropy coming in here. And so this is sort of quite surprising, or was surprising to us, is that we had a response, no matter how complicated the two-phase geometry is, one ended up with this sort of collapse at this given time. And that's sort of a little bit unusual because you've got two phases and each phase is basically going on its merry way, interacting with the other phase and remembering what's happening in the past. And then at these particular times, somehow something emerges and the bounds collapse and one can determine the volume fraction, essentially. You determine the volume fraction in an inverse way, just because these bounds are so tight when you know the volume fraction. So conversely, if you've measured the stress at that particular time, one can, okay, if the stress is measured to be there, the volume fraction must be the volume fraction of that red curve. Otherwise, for other values of the stress, there's an associated volume fraction. So that's basically what I was saying, that somehow one can tailor the time dependence of applied fields so that the response untangles in time and either becomes essentially independent of the microstructure or only depends upon the volume fractions of the phases. So the collapse is good. If it collapses without knowledge of the volume fraction, that can basically detect errors. And then when the bounds involve the volume fraction collapse, as I mentioned, one can determine the volume fraction for the response at the collapse times. So this naturally leads to questions. What's the math behind this? How should one choose the input field to ensure approximate or exact collapse? Then the question is, does it extend to bodies containing an inclusion and allow us to determine its volume? And can we determine the shape of the inclusion? So the first thing is it's not always the case with this stress relaxation experiment that the bounds collapse. It depends a little bit upon the response of the constituent phases. So here we're taking a this is stress relaxation, we're taking an elastic phase, and the second phase, however, has a relaxation curve that doesn't cross the first one, and then the bounds never actually collapse at any given time. However, we'll see how, but with suitably designed input fields, if for the same materials, one actually does get collapse at this time. Here, time t equals 0 is sort of arbitrary. That's just chosen as the point of collapse, and the fields or the responses also around for negative time. Anyway, so instead of linear systems, including viscoelasticity, one can consider an input function or applied field, if you like, that is composed of a set of frequencies with amplitudes at the different frequencies. However, the point I want to emphasize, at these frequencies, omega k, they can actually be complex. And so if you're not familiar with complex frequencies in a physical system, you just have to remember that a complex frequency corresponds to a signal which is increasing exponentially with time, perhaps slowly increasing with exponentially with time. But because the system is causal, you can always turn off the signal after a given time, after you've made the measurements. And so there's no problem physically with considering complex frequencies, at least provided they have an imaginary part in the upper half plane, so that they increase exponentially in time rather than having decreasing exponentially in time and having an infinite value in the infinite past. And then the response, so that our response will take this form here, where we still have the complex frequencies. We've got some weightings alpha k. F is a Markov function, and it depends upon some function z of omega k, and z of omega depends upon omega in some known way. So that will be sort of related to the material moduli. And then this function f is a Markov function. It has this integral representation here. That will be related to the measure will be related to the material geometry. And so now we're interested in getting results that are sort of independent of this measure here. So choosing the beta k such that the output function v of t at a given time, t equals t0, so t equals t0, these exponentials sort of vanish. At that time, t equals t0, v of t, you want that to be independent of the measure. And so specifically for the viscoelastic composite, U of t is the imposed average shear. V of t is the resultant average shear in the composite minus the shear stress that would be in pure phase 2. It's just convenient to take it that way. And then if we take the Fourier transforms, at frequency omega, V of omega is the effective. So here G2 and G1 are actually just the Fourier transforms of the integral kernels K1 and K2. G star of omega is the effective response at that frequency. Or alternatively, there's a K star of omega and G star of omega is its Fourier transform. But the important point is that G star of omega is actually an analytic function of G1 of omega and G2 of omega. Okay, that's something that dates back to work of David Bergman, myself, and Golden and Papanicolaou. Yeah. So this, and in fact, this ratio, G star of G2 minus 1 over 2f1 is actually a Markov function of the parameter z, which is g1 plus g2 over g2 minus g1. And because these g1 and g2 depend upon frequency, so too does z depend upon frequency. Okay, and the important point is that then the output function has the desired form, where now the amplitude A0 is just the volume fraction. F, capital F, that's our Markov function. And Z has this dependence upon omega, and I didn't talk about C. C entered in, where did C enter in? Yeah. We have the relationship between the alpha K and the beta K involving C. And this is what C is for the viscoelastic problem in terms of the shear modulus of the second phase. So now we arrive at a math problem. So if we take a Markov function and assume that the measure has unit mass, the question is can one find points z1 up to zm, not on the interval -1, 1. -1, 1 is where the measure is located, and complex constants alpha 1 up to alpha m, such that this linear combination is close to 1 for all probability measures mu. So in fact, that's sort of an old problem here. And I worked on this in the connected with composite materials, but there's nonlinear bounds correlating the possible values of f at these different points as the measure mu are well known. And so for given constants alpha 1 over alpha m, they actually provide optimal bounds on the range of values that S of mu takes as mu varies for given constants. So actually one knows the range of values that this can actually take, but that's not our focus. So this sort of range of values, I can sort of sketch what they sort of look like. So as more and more points, values of the function are known, you get a sequence of lens-shaped regions in the complex plane. Another way of sort of looking at that is some sort of multi-dimensional clam, sort of hard to picture things in multi-dimensions, but if we just had, say, the real part of f of z and the imaginary part of f of z, and f of z1 was known, then if f of z1 is known, then this sort of triplet of values, this is really complex, so this should be really two coordinates, those possible values of those four values must lie in some sort of clam-shaped region. If f of z is known, then that sort of corresponds to this cross-section here. If f of z is non-known, then that sort of corresponds to this projection down here. But the question is can one find an angle to view this multidimensional clam so it's almost flat when viewed from an appropriate direction? And then how do you identify those directions? So that's what we want. we want the supremum over measures of this linear combination, -1, to be very small. And now f depends linearly on the measure. And if we're taking the supremum over measures, we can restrict ourselves just to a delta function. And if we take a delta function, then f of a delta function measure, then f of zk just is basically 1 over lambda minus zk, where lambda is the point where the measure is concentrated. And so instead of dealing with this, one's left with this. And of course that that term there can be expressed as a ratio of 2 polynomials, and one's left with wanting this to be close to 0, and alternatively this to be close to 0, where p lambda of q lambda is the product of the denominators here, and p lambda is the associated numerator. Anyway, now this is sort of clear that it's now reduced to something of polynomial approximation, and after one's got p lambda of q lambda, the alpha k, which is the amplitudes associated with the signal, are then the residues of this rational function. So as it's polynomial approximation, it shouldn't be a surprise that one can use, say, Chebyshev approximation. And if one does that, one finds that indeed this supremum can be arbitrarily close to 1 if one chooses the alpha k to be given by this formula here in terms of the Chebyshev polynomials, and assuming that the zk are sufficiently far apart, sufficiently distant from the interval between -1 and 1. I actually had not defined that distance here. So at t equals t0 in our systems, this is the output, this is A0, and measuring v of t0 gives the system parameter A0, which will be the volume fraction. And so as c omega is known, so too are the amplitudes of the input signal. Sorry, this is the amplitudes of the input signal, and this is the amplitudes of the output signal, I think. Should double check on that. Anyway, not so important. Sorry, the beta of k are the input signals. So this gives you the amplitudes of the input signal. Okay, I think I forgot to delete that slide. And it's that one and that one. And you can extend this to the case of when you have n moments of the measure, and so that, for example, you've got moments m1 up to n-1, and you want to determine mn from measurements at a given time. And again, this is just polynomial approximation. And then in many systems, such as viscoelasticity, it's actually only the real part of v of t that has a physical significance, and that's easily treated. So in that case, the values of zk comes in pairs zk and zk plus 1. And and then one can take alpha k plus 1 is equal to alpha k bar, so that S of nu is real. So this gives you some sort of example. This is our Z of omega. This is our C of omega. Here we've got 3 complex frequencies for our input signal. And these are the results. And in each of these cases, the measure has unit mass. A0 corresponds to the volume fraction. M1 is sort of related. You get that if you have isotropy, basically. And so at this given time here, when you blow things up, you can see there's essentially exact correspondence of the output. And here's just another example, okay, different form of Z of omega. And again, at this time t equals 0, where we've chosen to try to get the bounds almost coincident, they are very almost consistent. So here we're using Chebyshev approximation and only getting approximate results, or essentially very accurate approximations to the volume fractions. But the question is, can one determine the volume fraction exactly? And the point, so here we have now a continuous spectrum of frequencies. So instead of having a sum here, one has an integral, where omega of S is now some trajectory in the frequency plane that and the trajectory lies in the upper half plane. S is just a real parameter that parameterizes that trajectory. And then the output, again, sort of takes this form involving, this is our coefficients now alpha of S, and this is again involving Markov functions. So everything is basically similar. Now Z depends upon omega still, and there's a trajectory now in the Z plane as S is varied. So now we have this theorem that if Z of omega S traces a curve as S increases from 1 to 0, and we let C bar be the curve traced by complex conjugate, that's because we just dealing with the real part of the output signal. So that's why we're sort of free to add C to C bar, if you like. And now assume that C union C bar is a closed curve encircling -1, 1. Then by choosing, for example, alpha S to be given by this formula here, where K could be 0, it's just a constant. Then we have that the output signal at the given time t0 is basically allows us to determine the volume fraction F1. And if K is 0, then this term is not there. If K is non-zero, then one can extract the first moment of the measure. So that's now an exact result, and I guess probably not surprisingly that it actually follows from the residue theorem, because now we have closed curves in the complex Z plane. But that was just for getting the response at a time t0. what was interesting is Ornella did the numerical experiments, and much to our surprise, she got the bounds collapsed for all times, not just times t equals t0, so that the volume fraction could be extracted by making measurements at any time. We thought that Ornella must have made a mistake, and she kept on checking it and coming back to the same result. And then we realized, she's right. And anyway, after that, actually Mihai came up with a proof that showed that you actually get this collapse for, that's a little bit technical, but now you actually have a collapse for any time. So now the V of t will be measure independent for all time. And so this is some numerical results. This is the Z plane. Here's our complex curve, our curve C. Here's C bar. And now, okay, we've got our responses of our two materials, and we've got some sort of trajectory in the frequency plane, which maps onto this trajectory in the Z plane. And these are the numerical results. This is for the, this is for the input as a function of time. And this is the output as a function of time. And so this is actually with the first moment known to. And so this is actually, in this case here, the response as a function of time only depends upon the first moment and the A0, not upon the responses at not on other moments of the measure. So a related problem one may be interested is correlating the response at M frequencies. That if A0 is known, can you tailor the input with M-1 frequencies so that at time t0, the output reproduces the response at the nth frequency? So here we're just dealing with, we're going back to the problem with a discrete set of complex frequencies. So here you can note that this is the so there's two possible models here. This is one for Z. This is sort of a second one for Z. And then at time t equals t0, you can recover the response, real part of V0 of t. This would actually be the response with just one complex frequency. These are the bounds that we get with an appropriate input signal. And so they sort of collapse at this time t equals 0. And here you get the same sort of collapse as well. So everything extends to the case when one has a matrix valued measure or operator valued measure. Again, it just reduces to polynomial approximation. And this is sort of an example of the matrix valued measure case. So for viscoelasticity, if I have anisotropic materials in 2 dimensions, the response is a vector, the stress vector. It's got components sigma 1, 1 and sigma 1, 2. and the measure is just a 2x2 matrix valued measure. And so now if I, let's see here, sort of run this simulation, you sort of see, so this blue region is sort of a bounding region, and then at a given time, the blue region almost shrinks to zero's size, and measurements at that time determine the volume fraction. So now what about bodies? Can one determine the volume or shape of a body, of an inclusion in a body from measurements at specific times? So I'm sure all of you are familiar with the Dirichlet-Neumann map. When one has a body with an inclusion, or here two inclusions. And for the Dirichlet-Neumann map, one specifies a certain boundary potential V naught of X, and then you measure the current flux at the boundary, and then the relationship between those is a linear relation, and that linear relation determines the Dirichlet-Neumann map. So the famous Calderon problem asks, can one uniquely determine the stress from the Dirichlet to Neumann map? And Sylvester and Ullmann proved one could. And then the key idea is to look for the response to boundary potentials V with K dot K equals 0. So this then becomes a harmonic potential satisfying Laplacian V equals 0. And they took in the limit where the modulus of K is very large. And that's termed the complex geometric optics limit. Of course, because K is very large and K is complex, that means it's actually got rapid variation, rapid decay away from the boundary, or rapid decay in one direction, or at least one direction. So for that reason, it's not so practical for determining the conductivity due to this rapid decay. So this is a old photo of this is Dick Cheney, with electrodes strapped around him. This is sort of a model for it, where one applies voltages at the different terminals, and then you measure the current through each terminal. And this is a inverse problem, sort of reconstructing the regions here. I guess this is meant to be a lungs, and this is sort of a heart. And anyway, so now as an input, see, we actually take a signal that if the material inside the body were homogeneous, would be given by this expression here, where E bar 0 is the gradient of V0. So V0 is what we'll have, the value of V0 at the boundary will be our prescribed potential. So we take V0 to be harmonic, but not necessarily with K having large amplitude. But we still want K dot K equals 0. We choose K1, K2 real. Here we're in 3 dimensions. And K3 to be given by this formula here to ensure that V naught's harmonic. And then you next take the inner product of the current field with the gradient of e to the I k prime of x, where k prime has the property that k prime dot k prime equals 0. And more precisely, you have these relationships here holding. And then by varying these Ks, keeping this relationship hold, you can actually find all Fourier components of D, allowing one to recover its shape, volume, and position. And so, okay, I don't have too much time, but this problem of the Dirichlet-Neumann map, it actually has exactly the same structure as the response in the theory of composites, or it can be mapped to a problem in the theory of composites, or what we call the abstract theory of composites. And so the effective tensor is then the Dirichlet to Neumann map. And instead of having a matrix valued measure, you have an operator valued measure. But everything goes through. Now, because the measure is operator valued, one can, instead of recovering the volume fraction, one recovers what's analogous to that is the solution to the Dirichlet-Neumann map for an almost homogeneous body. And so even if the material is not homogeneous, by choosing the input signal correctly, one gets this collapse at this time t equals t0, and from that one can recover all this information. So anyway, that's sort of skipped through that a little bit fast, but there's these references here that if you're interested, you might like to pursue. Thank you very much.
Thanks so much, Graeme, for a very nice talk. So the floor is open for questions. So please unmute yourself and ask questions if you have questions for Graeme.
Right. Can I ask some questions, Graeme?
Sure, of course.
Just maybe the other people don't know me. I'm Vincenzo Nesi. I was a student of Graeme when I was back at the PhD students at Curran. So this is my pleasure to be here. Thank you for inviting me. And I liked a lot your talk, because you sent me some reference. I was very worried that to read the many hundreds pages to start getting some feeling of it. But today I got a big kick. So thank you for that. I have one question about what you call, I think, theorem 2, where that was that when you draw that very nice contour around the -1,1 interval, and you stated a certain theorem, and I couldn't read, it was too fast, I couldn't read the statement, but what I wanted to ask you is the theorem saying that there exists such a path and that does the job, or that there exists infinitely many paths, or that's, I didn't get.
Oh, sure, yeah. There's infinitely many paths. That's yeah, so the
so when you move this contour, what is the you move the contour, and are there topological abstraction to get near to -1?
Right.
Or...
Yeah, so you have to avoid -1,1, and then for physical reasons, it's a well, it depends a little bit upon what you assume about the phases. If you have one phase which is non-dissipative or no, with no memory kernel, or purely elastic, say in viscoelastic phase, then it'll be the case that you've got Z of omega S, omega of S must lie in the upper half plane because you want your signals to increase with time. And then Z should also be in the upper half plane. But if I generally have a two-phase composite, that doesn't actually have to be the case. So the main there's several restrictions. The omega of S must lie in the upper half plane, right? So that implies certain restrictions on the contour. And then the other thing is that it can't intersect the points where the measure are, you know. So you have the measure in the Z plane lies between -1 and 1. It's on an interval. And so you want the trajectory to sort of loop around that measure. So you don't want it to be a closed curve that doesn't that doesn't contain any measure, or a curve that intersects the measure, you know.
Yeah, I understand that. But yeah, okay, thanks a lot.
You're welcome.
Any other questions for Graeme? So I was wondering, Graeme, so you stress sort of this very nice things bounce or with measurements in the time domain.
Yes.
Let's say that you're not able to, that you only can use a set of discrete real frequencies. Can you sort of use this insight to optimally construct then the probing signal?
Oh, you're saying that you want to recover your input signal from measurements of the output signal. Is that your question? Sorry.
Yeah, well, no, you strict yourself in terms of the probing, so you don't have the time domain measurements. Can you sort of say an optimal probing with just frequent harmonic response?
Oh, okay. Well, of course, we did a set of complex frequencies, you know. But you're talking about a signal frequency and then varying that frequency, I guess. Is that correct?
Yeah.
Yeah. Okay. So that's sort of an older problem for which there's that's sort of related to the first result of this sort of optimal bounds correlating these different things. Yeah, so if you have M frequencies and if you made measurements at each of those frequencies, that's a lot more measurements that we're doing now, you know. But you get much tighter bounds if you do it the way you're saying, you know. And so the point of this approach is to sort of minimize the number of measurements. Maybe I should have mentioned it, but you get this sort of nested sequence of lens-shaped regions, you know, and then that allows one to quite accurately determine the volume fraction, you know, or Elena Shikaev, you know, she recovers. You've got this integral representation. You've got this Markov function involving a measure. So Elena tries to recover the measure from the measurements at a discrete set of frequencies, you know, and then it's a different measure that I have here. There's sort of a factor of the volume fraction essentially. So from the integral of her or the measure that she uses, one determines the volume fraction, you know. But that's sort of, in some sense, that's sort of older results, and this is sort of new approach, you know.
Any other questions for Graeme? Otherwise, let's thank this Graeme again for a very nice talk, nice techniques.
Well, thank you for listening.